remotely. Oh, maybe it's better if someone else does it.
And you're live.
Visio Imag. Okay, yeah. Sophie just joined, I think.
You hear us, Sophie?
Oui, and you?
Yes.
Ok, sorry.
On t'entend très bien. Tu es un petit peu flou, mais c'est tout.
Ouais, je sais. Là,
Pas très grave.
la caméra n'arrive pas à se régler toute seule et je.
That's fine. Thank you very much. It's all right. Okay, Mathieu,
we can begin, yes. Good afternoon all. I'm Mathieu Paquier. I'm professor at the UBO, the University of Brest. And I'm happy to share the HDR defense of Nicolas. It's quite unusual defense because we are totally remote because Nicolas has the COVID. But fortunately, I think he's better and he's able to defend his HDR. Well, the title of the HDR is Interdisciplinary Approaches for Neuroscience, Artificial Intelligence and Sound. And I'm going to introduce the committee. First, the reviewers. Dimitri Vandeville from the École Polytechnique Fédérale de Lausanne, Peter Wust from the House University, Geoffroy Peters from Telecom Paris, and also Sophia Char from the University of Grenoble, and Serge Tiemsit from the Brest University. Well, Nicolas, you have 45 minutes, and after that, we will ask you some questions. Let's go.
Thank you very much, Mathieu, for the introduction. So, can anyone confirm you can see my screen?
Yes.
Okay. So, thank you very much, and I'm really happy to be defending today. So not in optimal conditions, of course, but still, this is a very important event for me, and I'm happy to do this. I want to thank the members of the jury for accepting the invitation and the reviewers for taking a lot of time to review this work. And I will talk to you today about interdisciplinary approaches for neurosciences, artificial intelligence, and sound. So this presentation will be structured in the following way. I will start with a short introduction where I will explain where I come from, and followed by breaking down the different contributions of this thesis. So first of all, I have a quite unusual background. I was trained as a musician initially until about 1998. I was at the Music Conservatory in Dijon in France, and I studied the violin and classical percussion as well as music theory. And I switched to major science studies afterwards. Ended up doing an electrical engineering master, diplôme d'ingénieur, at NCA, which is an electronics school, and graduated in 2005. I decided to embark into a PhD in electronical engineering, which ended in 2008. And during my PhD, I did some hardware implementations of convolutional neural networks. So that was more like an electronics PhD with like embedded systems and parallel architecture. I will talk about it a little bit in the defense afterwards. I worked in the industry for a little while. I'm not going to talk about it more here, but I did like a 1.5-year gap. And then I decided to go back to research. I embarked into postdoctoral projects in cognitive neurosciences. And I was really, really lucky because I was able to join the EBRAMUS project. So EBRAMUS stands for Europe, Brain and Music. And it was a great project that was between 2010 and 2013. And I was a 2 years postdoc in this project. So we'll talk about the contributions I've done during this project later. I joined the Max Planck Institute for 1 year after that, followed by a 2 years postdoc in Goldsmiths, University of London. And I ended up in Telecom Bretagne for a bit less than a year postdoc before getting an associate professor position here since July 2016. So initially part of the NECODE team with a principal investigator, Claude Béroux, until 2017. And then we created the BRAIN project with Vincent Gripon. So in terms of my activities as an associate professor, just to recapitulate and summarize things quickly, in terms of supervision activities, as a PhD advisor, 3 of my students have already defended and 7 are ongoing. I also supervise 4 postdocs, and there's 1 currently ongoing, and 3 master students, so like 6 months projects. 1 is ongoing as well, and about 21 research interns. So these 21 interns are like short interns, like 2 months to 4 months maximum, and typically first or second year master students or engineering school students. In terms of funding, so I didn't include the exact amounts, but just to give a rough idea in terms of years. So I was able to secure about a total, like cumulative total of 4 years of postdoctoral funding, which ended up being able to work on graph signal processing, I'm going to talk about later on. Also secured some public funding for PhD, and so 3 half PhDs, as well as private funding as PI or co-PI, and also some private funding for PhD, half a PhD. In terms of teaching, so I'm responsible for 2 courses on artificial intelligence. The first one is an Introduction to Artificial Intelligence course, which is a very general purpose course. And the second one is an Efficient Deep Learning course, which I co-lead with Mathieu Leonardo. And it's a course which is quite original because we try to teach students how to understand deep learning better in order to make it more lightweight and more efficient. I also contribute to biomedical signal processing, and as well as computer science courses and electronics. In terms of teaching, I was also invited at the University of Brest, and I mostly teach neuroscience there, and especially functional MRI. So introduction to functional MRI, as well as brain plasticity measured by functional connectivity using functional MRI, as well as clinical applications of functional MRI analysis in master clinical neuroscience. So these teaching activities totalize to about 200 hours per year. And to finish this short CV, I just extracted the Google Scholar impact page. So I have about like a bit more than 1,000 citations so far with an index of 16, and it's still growing, hopefully. So that finishes my short introduction. So I will now try to give an overview of the work. So this has been quite of a challenge because, of course, it's very difficult to include everything and also to find a coherent narrative, but I've tried my best to do so. And there are some of the things that are in the manuscript that I will not cover here. And instead, I propose you this kind of overview, which is actually a kind of a graphical overview. So if we consider the subject of interest here, let's say the main subject of interest is sound. So if we consider first different kinds of sound sources, so here is a possible list of different sources of sound. So we can see sound coming from objects, from animals, from humans, from humans playing music, humans listening to music, or other sources and sounds such as vehicles, planes, cars, trains, or also sounds from nature, from earth, like wind, waves, rivers, rain, or even maybe sounds from organs like heart or breathing. So these different sources have in common the fact that they're able to displace some air and generate some sound. We can also be interested in looking at the interactions between the interactions given by sound with organisms and the underlying brain mechanisms. So sound has an effect on all living beings and also on environments. In terms of the human brain, we are interested in looking at auditory perception. So how does the human brain comprehend sound? And also, how is it possible that the human brain can imagine sound or imagine music? So this is one mechanism we're going to look into in detail, which is called musical imagery. So the fact to recreate mentally sound in the absence of sound stimulation. We're also interested in temporal perception, so temporal processing and the processing of temporal regularity, which is coming from auditory input. So auditory stimuli can have some temporal properties, and the brain has to comprehend these temporal properties in some way to be able to predict what's coming next. Other mechanisms that are important are mechanisms of sensorimotor synchronization. So the fact that humans should be able to move in time with respect to the environment and with respect to the sound that they hear and respond with their movement appropriately. And another kind of interactions and organisms that we can look at is the effect of sound on ecosystem or on cities. And how are we going to study these things? We're going to study them with different kind of methods. So here I describe methods from neuroimaging, from brain imaging, as well as methods from machine learning and from graph signal processing. So in a nutshell, one method that we will rely on a lot is functional MRI, so magnetic resonance imaging, which enables to measure and image the brain in a very high spatial resolution. And once we have a high resolution measurement of the brain, we can divide the brain into regions of interest, which can then become a graph with nodes and edges corresponding to the connectivity between brain regions. Then we can use tools from graph signal processing to decompose the graph and to try to understand signals as a function of connectivity. Another important tool here is deep learning. I will get into more detail later, but essentially decomposing complex data into a format which enables to take easy decisions. We're also interested into optimizing complex algorithms for energy consumption and for optimization on hardware. So putting all these pieces together gives the following graphical overview, where you have the sound sources on the top, the mechanisms and the organisms with their interactions on the bottom left, and the methods on the bottom right. So the first chapter in this presentation is going to be about auditory cognitive neurosciences, which is the science of trying to understand how the brain processes sound, essentially. And we're going to look into two subjects, first one being sensorimotor synchronization and Parkinson's disease, and the second one is involuntary musical imagery. So sensorimotor synchronization, or SMS, can be defined as the ability to perform appropriately timed movement adapted to the environment. So this is an ability that is widespread, that is needed to live for daily life. I mean, we need to synchronize our movement in many of our daily activities just for being able to have a conversation or being able to walk, being able to avoid dangers or to follow a path. Of course, more complex coordination activities like playing sports or playing music. And it relies on brain networks, obviously, and the literature, like research in neurosciences, indicates that, of course, the motor and the premotor networks are needed for sensorimotor synchronization, but we also, of course, need sensory areas like the auditory cortices, and more critically, also subcortical areas like the basal ganglia, which are needed for loops of regulation and also for being able to predict upcoming movements and upcoming stimuli. And these networks of sensorimotor synchronization and of temporal processing can be disturbed by neurological conditions. So in a way, studying sensorimotor synchronization can be seen as a framework to study how the brain processes temporal information. So the fact that we know that certain conditions are disturbed, have like detrimental sensorimotor synchronization, is an indication of the mechanisms that are important for sensorimotor synchronization. And another piece of evidence that we're interested in is that we also know that sensorimotor synchronization can have beneficial effects in certain conditions like Parkinson's disease by using rhythm for motor rehabilitation. So this is the two main objects of studies that we're going to look at today in this presentation. And this is part of the work I done when I was part of the eBrammers project. So the methods to measure sensorimotor synchronization are very simple. It is mostly based on measuring different movements from effectors from humans. And typically, we can measure it using hands. So tapping, participants can be asked to tap using their hands or using sticks, like drumming. But we can also measure sensorimotor synchronization by walking, also by finger tapping, or using accelerometers. And there are different types of paradigms that can be used. So what is called the self-paced tapping is a paradigm in which the subject is asked to tap regularly, but without any external stimulation. So without any external pacing signal. So a self-paced tapping is just tapping regularly, and the subject chooses the rate at which he taps. The second rule is in paced tapping, there is an external stimulus like a metronome, and the instruction for the subject is to tap as closely as possible to the stimulus. So it's like tapping to a metronome and trying to synchronize to the metronome. And a final very famous paradigm used in the sensorimotor synchronization literature is the synchronization continuation paradigm, which begins exactly like a paced tapping, but then the stimulus stops and the participant has to continue tapping at the same rate. So it is a paradigm that is useful to measure whether participants are able to sustain the same rate. And we actually observe in certain conditions that once the stimulus is dropped, once the participants have to continue tapping, they have problems in the continuation phase and not necessarily in the synchronization phase. So these are the main methods used for sensorimotor synchronization. Another method that we're going to use to investigate temporal processing is electroencephalography. So electroencephalography is the study of the brain activity using the electrical signal at the scalp level. And in this case, we are interested in event-related potentials, which is the study of time-locked responses averaged across many, many repetitions of the same stimuli or stimuli of different conditions. And it corresponds to average deviations of brain responses at the scalp level. So in the first contribution in 2012, and also confirmed in a larger paper in 2016, with Simone Della Bella, we introduced the Basta, which stands for the Battery for the Assessment of Auditory, Sensorimotor, and Timing Abilities. And Basta is a battery of tasks to assess temporal and beat perception and sensorimotor synchronization. So Basta is composed of different tasks. It's composed of perceptual tasks like duration discrimination or anisochrony detection, which consists in detecting a very small temporal gap, as well as a beat perception task, which is called the BAT. And here I will mostly talk about the production tasks, which are tapping tasks, the same one that I described in the previous slide. So unpaced tapping or self-paced tapping, so spontaneous tapping rate, paced tapping with metronome and music, synchronization continuation, as well as adaptive tapping, which is a variant of synchronization continuation, but with a tempo change. So the Basta was used, and I'm going to describe how we used it. We actually used it to measure synchronization in Parkinson's disease and the effect of therapy. So this is part of the very large project I was part of in eBrammers. We studied a program of gait rehabilitation in Parkinson's disease using rhythm. So patients with Parkinson's disease actually have lots of problems walking. They have like very, very small steps, and they don't actually really do steps anymore. They have a very, very high risk of falling, and their steps are very, very shallow. in a way. And it is already well known that rhythmical cues can be used to help rehabilitation of gait, so walking rehabilitation. This has been shown in large meta-analysis, but little is known about the neural correlates. So we tried to see whether there is a link also with timing deficits that are also quite documented in Parkinson's disease. So patients with Parkinson's disease have issues with perception of time and sensorimotor synchronization. So we designed this study in which we had a pre-test where we assessed the optimal stimulation speed for patients. So we measured how fast they could walk, and we tried to stimulate them with a metronome, with a music, with an embedded metronome, slightly faster or slightly slower than their walking speed. And we choose the tempos that lead to the best immediate effect. And then they went into a therapy, 3 sessions per week during 1 month. And each session, they did walking exercise with personalized stimulus for 1 hour. So this stimulus is like music with metronome. And we administered the Basta, so the battery of tests, before the therapy, immediately after, and 1 month follow-up. And we found that actually the tapping abilities were impacted by the therapy. So first, we also found that before the therapy, patients were impaired in terms of tapping, so they were significantly more variable than controls, and their impairment were slightly reduced after the therapy and at follow-up as well, where they were back to the level of controls. So this is a very important study that we published in 2014, and is probably still one of the most cited papers in the papers I published recently. So in another related study, we tried to understand how does the brain process temporal regularity in healthy subjects, and as well as in Parkinson's disease patients. So this was done using electroencephalography, using EEG and event-related potentials. And the paradigm was as follows. So it is a simple oddball paradigm. So an oddball paradigm with pitch deviance, where we have like 80% of tones which are the same pitch, and 20% which are different pitch. And the task is very simple. The subjects just have to count the number of deviants, just to keep their attention. Actually, we do this 2 times. We do it once if with a completely temporally regular situation, which each tone occurs every 900 milliseconds. And in another condition, there is like an irregular temporal onset of the tones. So the exact moment in which the tones arrive are unpredictable. And using this paradigm, we can study the effect of temporal regularity and predictability on the brain responses. And we found out that very early event-related potentials were modulated. So this paradigm was introduced by Michael Schwarzer, who was a postdoc, and I collaborated on the analysis and the deployment on Parkinson's disease patients of this paradigm. So the P50 and the N1 are 2 early event-related components that are evoked after sound. And we showed that the amplitude of this component was modulated by temporal regularity. And most importantly, we showed that it was only modulated on controls and not on patients, which indicates that patients' brain responses might be impaired as a function of temporal regularity. So this is one way to investigate how the brain processes temporal regularity and compare healthy subjects and patients. So as a conclusion of this part, we've introduced the Basta. We showed that there were timing deficits in patients with Parkinson's disease, and we also showed that there is clear effects of rhythm-based gait rehabilitation, and that neural responses to temporal regularity were affected by Parkinson's disease. So this led to a few publications that I listed here as well. And this was done mostly during my postdoc between 2010 and 2015. So I will now talk about the second part, which is involuntary musical imagery. So involuntary musical imagery can be defined as short loops of imagined music that emerge spontaneously in the absence of immediate auditory stimulus and without conscious control. So INMI is widespread. They are widespread in the general population. It's been shown that 90% of people have them at least once a week. So it's a very common situation. It's just having music in your head, and almost everyone has that. It's been shown to be triggered by recent exposure, attentional states, or other kind of cues. Most people like it. Some people hate it. It's been shown that it's linked to personality as well. And little is known about the neural correlates as well of INME. So and also the function served by this mechanism is still uncertain. So we don't really know why the brain does that. So in the first study, we've used MRI. So I will talk only in this presentation about structural MRI, but in the manuscript, I describe also some first hint we have with resting state functional MRI. So structural MRI is based on images produced from MRI using T1 weighted images, which give a very good contrast of the gray matter. And once we have T1 weighted images, we can do segmentation of different tissue types and measure gray matter volume and cortical thickness. So this is the main outcome measures that we can use to measure actually individual variability in gray matter and brain structure, essentially. So we use structural MRI to see if there is a link between brain structure and involuntary musical imagery. So we found out in a paper published in 2015 that the frequency of INME, so how often people have music in their head, was related to cortical thickness in many different brain areas, like the left angular gyrus, as well as the right inferior frontal gyrus, the right superior temporal gyrus, as well as the right angular ACC. We also found out that gray matter volume in the right temporal pole was related to how much people were disturbed by involuntary musical imagery, and also that the gray matter volume in the parahippocapal cortex was related to how much people feel helped by INME, so how much they enjoy having music in their head. So this was done using a questionnaire and relating that to 44 participants. So it's a cross-sectional study. So it's based on the average experience of INME and not on individual episodes of having music in their head. But still, it gives an idea on the possible neural correlates of involuntary musical imagery. We were able to show that there are individual differences in brain structure of auditory areas, mostly, with relation to the frequency of INME, so how often people have music in their head. And we also saw a lot of areas of the default mode network, which suggest a possible link with other functions related to self-generated thoughts. So this concludes my first part about auditory cognitive neuroscience. So I will now switch to the second part of this presentation, which is about machine learning and graph signal processing. So there's quite a few new methods to introduce. So I will first spend some time to do that. So first, what is machine learning and deep learning? So machine learning could be defined as a process of inferring a function, a complex function, using only examples of inputs and outputs. So we most of the time work in a paradigm what is called supervised, which means that we have examples of inputs and outputs of what we're trying to measure, and we have to find ways to infer this function. It's a very difficult problem, obviously, because it's a nilpotent problem. There's an infinity of potential solutions, and one way to do so, to solve this problem or to address this problem, is to seek for solutions with a particular form. This is what we do when we do deep learning, because we are looking for particular solutions which have certain characteristics. So instead of trying to infer directly one big function, we actually express the solution as an assembly of small functions, which are called layers, or also call them atomic functions. So this is a compositional approach. There is a way to tune all these atomic functions all together using what is called end-to-end learning, where actually there is no pre-processing, working directly from the input data. And also recent progresses in optimization algorithms enable to actually use variants of stochastic gradient descent to optimize all these functions together using differentiable algorithmic. So it is the main principle to show what it looks like graphically. And in the case of audio, which is our main interest today, let's consider the following picture. So on the left side, we have a raw audio waveform that is shown vertically. So this is a unidimensional signal, which has, let's say, for example, a sampling rate of 22 kilohertz. And when trying to learn a deep learning architecture on audio waveforms, what we typically do is we try to find layers which are a very simple composition of 1D convolutions, subsampling, and a nonlinearity. So a 1D convolution is a very simple filter, which is just a set of coefficients which will filter out some characteristic of the input signal. Subsampling is typically just an average, a local average, which will reduce the size. So typically divide by 2 the size of the signal, or the temporal resolution. And the nonlinearity is like typically the most widely used is the restricted linear unit, which is just filtering out the negative values and keeping only the positive. And what is typically done here is we learn an increasing number of features, which are these 1D convolution layers. So on the first step, we learn 32 filters, then 64, 128, etc., up until 1024. And by decreasing the temporal resolution, so we begin with like a very high temporal resolution, but just one dimension, and we end with a very low temporal resolution, like 0.5 hertz, but with lots of features, like 1024 features. So that's the principle, is to learn a very complex decomposition, which is actually a high dimensional space, which enables to do some operations that are not possible to do directly on the raw signal. So that's the core principle in deep learning for audio. And the problem when trying to do so is that we can easily end up with architectures which have a lot of parameters. So I put here 2 pictures. On the bottom left is a recent trend in the four last years in large language models. So 4 years ago, in 2018, the largest language model was Elmo with 94 million parameters. And today we count in hundreds of billions of parameters. So that has become irreasonably huge. And on the right side, I also show a similar picture of almost state-of-the-art, not really state-of-the-art, but still like quite good architectures on the dataset named AudioSet, which is a large-scale audio deep learning benchmark. And we still have to count in like dozens to 100 million parameters to have like a good performances on this kind of problem. So when I refer to efficient deep learning, the biggest motivation of this kind of work is to try to reduce the computational and memory complexity of deep learning architectures. So I have contributed to this question. I've contributed in my PhD work a long time ago by investigating parallel architectures for convolutional neural networks that was done in between 2005 and 2008. And I also contributed as a supervisor of the thesis of Ruti Boukliassen, who won 2 PhD prizes in 2020. And he proposed architectures for quantized guided bit pruning, as well as incremental learning. And I also supervised another project by an intern, Nicolas, on binaural raw waveforms for auditory scene classification, which was also trying to optimize the parameter count. So that's for the question of efficient deep learning. Now I will dive into the other subject, which is graph signal processing for neuroimaging. So this project is probably my biggest contribution since I joined IMT Atlantic, and is based around the very recent framework of graph signal processing, which was proposed in the early 2010s and popularized by a few seminal papers in 2013 by Schumann, notably. And I will spend some time to break down this figure to explain what this is. So this figure is taken from a paper we published with Julia Lioy, which recently joined our team as well as an assistant professor. And the idea is the following. So in panel A, we have measurements of brain activity as well as brain connectivity. So we can measure brain activity using functional MRI or electroencephalography. We can measure brain connectivity using diffusion MRI, which measures white matter tracts, white matter anatomical connectivity. So as soon as we have brain connectivity and division of the brain in brain regions, we can build a brain graph. A graph is a set of vertices and edges. So in this case, the vertices are the brain regions, and the edges are the connectivity between the brain regions. So this connectivity can be measured using diffusion MRI, using anatomical connectivity, But it can also be measured using functional connectivity, like correlation, like statistical connectivity between regions. As soon as we have a graph, we can describe it using graph theory. So we can describe it using an adjacency matrix, which is just a matrix form of the graph, which describes the weight, the strength of connection between every pair of regions. And there are several measures that can be derived from this adjacency matrix, like communities, like defining subgraphs, like small graphs in the graph, or finding shortest paths between two regions, or finding some nodes, some vertices which have hubs, which are like important nodes in the network, which can be called hubs. So that's graph theory. The next step is graph spectral theory, which is based on the eigen decomposition of the adjacency matrix or other matrices derived from the adjacency matrix, like the Laplacian matrix. So it's essentially diagonalization, eigenvector decomposition. And it's possible because the adjacency matrix, in our case, is symmetrical, because we consider only unweighted, we consider only undirected graphs. So this is always possible. We can find eigenvectors. And these eigenvectors actually, in the neuroscience literature recently, they have been referred to as gradients because, as it turned out, they have important properties and they can explain functional organization of the brain, especially when we consider what is called functional gradients, which are a decomposition of the resting state graph. So if we decompose the resting state graph, we can actually see this kind of eigenvectors by decomposing the matrix of resting state. And this eigenvector is functionally meaningful. This has been shown by Margulis in 2016, and it opened a new field, which is the analysis of connectivity gradients. So once we have graph spectral theory, we have sets of vectors, we have eigenvectors, we can define graph signal processing. So essentially, the idea underlying graph signal processing is to use the graph and consider a signal on the graph, which means a signal value on each vertex of the graph. And once we have that, we can define tools from signal processing, like Fourier transform or wavelets, using the properties of the graph. And we can define notions of graph frequencies, like low graph frequencies or high graph frequencies. So for example, a low frequency would be typically interpreted as a diffusion pattern, like a left hemisphere to right hemisphere diffusion pattern, which would be a dominant connectivity pattern, for example, in anatomical connectivity. And we can also define high frequency pattern, which would be more like very localized signal. So we've contributed quite a lot to graph signal processing. And one of the things we've done is to show that it's possible to use it as feature extraction and do supervised learning afterwards. So we've done several contributions. I will just talk about one here quickly, which is to do that for detecting autism in a benchmark of autism diagnosis, which is called the ABIDE database. And we've actually shown that our solution was not necessarily the most competitive in terms of accuracy, but it was actually a very simple solution in terms of number of features. Like the size of the solution was quite reasonable and was able to generalize well on a very large pool of subjects. We've also shown that we can use GSP for feature extraction in more classical brain decoding tasks. In a more recent contribution, one of our students in first year PhD, Yassine El Waidi, has shown that actually we can use graph signal processing to define a convolution operator in the spectral domain and define a deep learning architecture based on this graph spectral convolution block. And he has trained this architecture on very large brain decoding benchmark, the Human Connectome project. And he has shown that when using pruning, by simplifying the network, so by pruning the different frequencies, he was able to identify which are the most important graph frequencies. And graph frequencies can be seen actually as diffusion patterns. And this is what you see here is the 4 most important graph frequencies. So these are quite typical because this is like mostly like a visual network. This is mostly an auditory network. And we can see also motor and default mode network, which are like 4 very important networks, which are able to be combined to decode any task pretty much. So I move on to the fourth part, which is more an opening, but still describes some work in progress. So the method I have to introduce here is very important because this is the one that will be used in most of the work that I describe until from now on. So the method I describe here is called transfer learning, and also fine tuning, which is quite a subtle variation from it. So the idea of transfer learning is to actually consider a deep learning network like that has been trained on one data set. So it has been pre-trained. We'll consider it as a backbone, and we want to train a new data set by reusing the weights of this first trained network. So we have this backbone, we're going to keep it and try to train a downstream network. So it's really the idea of reusing deep learning for something else. So one data set, we use just one part of the network and we train another network after it, like a downstream classifier. And there's two use cases: fine-tuning, in which everything is retrained, or transfer learning, in which only the downstream network is trained. So it's an interesting case to study generalization. Is it possible to use something that has been trained for a task and try to make it generalized to another task? And I will show that we have a quite interesting use cases to consider using transfer learning. So one thing I'm become more and more interested in is what I call ecological conditions. So it can seem a little weird said like this, and the reason for that is that we should not confuse ecological with environmentalism. So what I mean by that is that I'm not talking about protecting the environment or reducing carbon emission or anything like that. What I mean is that I consider ecology as like the primal sense of the word, which is the study of the relationships between living organisms, including humans, and their environment. And what I would call ecological conditions in this case is it possible to recreate habitats or situations using appropriate experimental settings or naturalistic stimuli? So in case of cognitive neurosciences, realistic stimuli would be something, ecological conditions would be to use more realistic stimuli, like recorded music instead of computer-generated music, or maybe perform out-of-laboratory experiments. Other example could be bioacoustics, which is the study of sounds produced by living beings in their natural habitat, or ecoacoustics, which would be ecological studies using acoustics, so interactions between beings. And it's a research question, it's a set of research questions that is well adapted to transfer learning because it's a use case in which we have to generalize to something very complex. So transfer learning can be used to disentangle complexity of these natural habitats or ecosystems. And we can maybe try to use pre-trained networks to make them generalize to something else. And maybe we can also try to build deep learning networks as models of complex systems and their interactions. So that's one of the ambitions here. Going to quickly try to describe a few projects in which we try to do that. So the first one is a project that was launched in 2020, which is called Silent Cities. And it's the study of the urban soundscapes in 2020 with the effect of lockdown due to COVID-19. So the idea is to study the impact of lockdown on the socio ecosystems, because as like all human activity shut down, then there is no trains, no cars, no planes anymore. So a lot less sound from humans. So we reached out to the community of people who do ecoacoustics, and we managed to actually deploy 400 video recorders in 50 different countries, recording almost continuously, and that ended up like being a massive amount of data. And we actually use transfer learning for sound event recognition. So this is a contribution that we do for the ecoacoustic community. And there is a data paper in preparation, which is an open science contribution. And we can test many different questions in ecoacoustics, also in machine learning. Another application of transfer learning in ecological setting is a collaboration with the company Also AI that was recently launched in the case of the PhD project of Ilyas Moumad. So the idea is to use sound to do some aid of diagnosis of sleep apnea. So we use recordings coming from the university hospital, and we try to detect sleep apnea using only sound recording, but we have annotations coming from other physiological recordings. And the ambition is to be able to have like an AI-assisted diagnosis, as also AI has deployed like lots of sound recorder devices in elderly houses' bedrooms to detect some events, like to help also the personnel there. So that's another application in an ecological setting. And the final application I will talk about before concluding this presentation is a very ambitious project about encoding models and brain-like representations for AI. So encoding models of auditory brain activity, I'm going to explain what I mean by encoding models. But first, if we look at auditory cognition in general using functional MRI, so here this picture was generated using NeuroQuery by just looking for the word auditory. So this is an aggregation of like all auditory studies, and very, very reliably, we can see the superior temporal gyrus, so like the temporal cortex, upper part, a little bit anterior, that is activated, which is mostly like the summary of studies where you would compare just the sound versus the silence. And since 2010, people also do some machine learning and decoding approaches, trying to characterize better what's happening with this kind of with this area. What we mean by encoding model is more like the reverse. We want to see whether it's possible to actually model the activity in the auditory cortex using the stimulus. So that's the idea of the encoding model, predicting brain activity from the stimulus. And the ambition behind that is to be able to model new stimuli afterwards, because an encoding model, the input is the stimulus. So if you're able to model a set of stimulus, if your model is good, you take new sets of stimuli and you can predict brain activities. This will serve as kind of confirmatory data when you're trying to test hypotheses. So we are doing this in the case of a very large project, which is called the Courtois Neuromod project, which is a collaboration with the University of Montreal. And it involves 6 human subjects. And it's a very, very dense collection of data. It's like 500 of fMRI per subject. Sorry for the typo. So 500 fMRI per subject, which is like about 1.5 hours per week for several years for 6 subjects. They do lots of different things. They've watched some films, they watched the whole Friends series, they've seen images, they've played video games. So there's a quite large diversity of tasks. And the goal of the project is to use deep learning to model brain activity, and especially using encoding models. So in the case of in the context of the PhD project of Maël Freteau, co-supervised with Pierre Bellec at the University of Montreal, we are using fine-tuning of a pre-trained audio deep network. And we show that actually using about 40 hours of MRI on individual subjects, we are able to fine-tune networks to predict brain activity from 40 hours of fMRI data with quite a good reconstruction rate, like a correlation score of about 0.5 to 0.6 in the best cases. So I will not go into the detail of this to be able to conclude with more time, but I can answer more questions about this part if needed. So I will try to summarize all the aspects and give some outlook on the possible direction that this work can take. So I will start back from the graphical overview. So just to recapitulate once again, on the top part, you have the sound sources. On the bottom left part, you have the mechanisms and the organisms and the interactions between them. And on the right part, you have the methods. So I will break down the different things we've talked about by removing and showing some things. So in Parkinson's disease, we've shown that timing abilities were linked to rehabilitation outcomes and basal ganglia circuits. We've shown this by using a cueing program, so auditory cueing program and gait rehabilitation, and coupled that with a battery of tasks. And we've shown some beneficial effects, which means that after the therapy, participants had actually less variability in tapping. And in other studies, we've also shown some link between sensorimotor abilities and the outcomes of therapy themselves. We've also showed that we can study temporal processing using EEG. In terms of involuntary musical imagery, we were able to show the role of auditory, parahippocampal, and default mode network. We've shown some very promising results on encoding models of auditory brain activity by showing that fine-tuning audio deep learning networks can help to model brain activity using fMRI, using large quantity of fMRI data on individual subjects. We've shown the potential of graph signal processing for neuroimaging, and especially the relevance of graph Fourier features for decoding brain activity. also have shown some contributions in efficient deep learning, and especially the importance of data augmentation and binaural audio, which is mostly described in the manuscript. Just mention it here. I've quickly mentioned the Silent Cities project, which is kind of a large-scale transfer learning application on very, very complex, non-identically distributed data and like real-world data on like very large amount of data, which here encompasses like all the different sound sources. And as perspectives, I will just mention a few things. So the three first points here are ongoing projects of several PhD students that are currently in the group. So I'm interested in multimodal graph signal processing. This is currently investigated by Venkatesh Subramani, who joined the team in January, and also another student that will join the team in October, Alex Lamoureux. And they're both going to look at how to use both EEG and fMRI in graph signal processing by trying to exploit brain graphs to understand the interaction between modalities. And it's also a way to look at the coupling between function and structure. Another topic that I'm interested in is self-supervised learning. And Ilyas Moumad is currently looking at this in terms of audio, trying to see whether we can learn efficient deep learning approaches using self-supervised learning. Brain-computer interfaces is also a subject of interest, and brain decoding using graphs and few-shot learning. This is the project of Yassine El-Waidi. And in the future, in the next couple of years, or maybe in a little bit more long term, I'm interested into developing more ecological studies in cognitive neurosciences to trying to continue using machine learning or just like ecological settings to try to study beings in their natural environment in situations which are more realistic. I'm interested into trying to understand better what kind of inductive biases we can use. So can we inspire research in artificial intelligence from the different things I've talked about, like temporal processing in the brain, predictive properties, or even maybe musical imagery? Can this be used to better understand how we can train deep networks? And also would like to try to investigate how to learn more generalistic auditory representations by taking inspiration from the auditory system. So I want to thank my collaborators, Vincent Grippon, Mathieu Leonardo, Julia Leroy, Michel Ezekiel, Claude Béraud, and other colleagues and collaborators. And with this, I want to say thank you, and I will welcome your questions now.
Thank you, Nicolas. Now it's the time for questions. As we discuss, I will give the floor to each members of the committee in turn, but if one of them want to add something to a question of another member of the committee or to an answer of Nicolas, it's possible to, because it's HDR defense and we are not forced to be as formal as a PhD defense. Well, we can begin maybe with Dimitri, with the reviewers. Dimitri?
Thank you, Mathieu. Thank you for giving me the opportunity to ask questions. First of all, let me thank Nicolas for the fantastic presentation. It's really a great pleasure to be part of your HDR, even if it's somewhat in an exceptional setting today. But I mean, we're getting used to that. And the first thing I like to really mention is that I think it's fantastic that you have such an atypical career path as you showed us. And I think we really need more people like you in the field because you bring in a lot of diversity and creativity that we need, you know, to bring this, I would say, by default, interdisciplinary community of brain research together and inspire each other. So you're certainly one of the very inspirational persons in this community. So thank you very much for that. Maybe to say on the formal side, as I mentioned in my report, I think you fulfill and exceed all the requirements for an HDR. So I mean, I just want to underline that. And so therefore, I have a couple of questions, but they are more meant to be a starting point for discussion and to give you the opportunity to maybe, you know, put some more extensive considerations on what you showed us already.
Sure.
So let me maybe have a look at my notes. Okay, so I mean the graph signal processing is a very exciting field, and then you showed that, and you have already various ways in mind. Well, you applied it already in various ways, but you have also various ways in mind to further extend it. And my question to you would be, so as you have said us, you need to define a graph, you need to consider graph signals, so signals on that graph, and you can do that in many different ways. And so basically, you need to define the scale in space and in time that you want to consider. And again, you can do that in many different ways, like choosing your porcellation, which could be coarse, medium scale, or very fine grained. You could go on a mesh in a volume. As you showed, you could do structural connectome, functional connectome. So according to you, what would be ideally the best way to go? Should we push these brain graphs to very high resolution? What is your take on that?
So I think there is a quite inconsistent set of results right now that still needs some work to be reconciled or to be figured out. So what I mean is that when we look at what graph signal processing is supposed to do, we would hope, in a way, we would have the hypothesis that it would be ideal for multimodal data fusion. It would be ideal to actually use things from different modalities. So one of the things we try to do is, for example, to use the anatomical graph, which comes from diffusion, MRI, so like white matter connectivity, and to try to analyze functional MRI signals on top of it. So we already know from other studies that the two kinds of connectivity, so anatomical connectivity and resting state functional connectivity, we already know that they don't coincide completely. We know that there are some links that exist with one and don't exist with the other one. So some people would say, well, there is no point in considering functional MRI signals and anatomical connectivity because we know there's a discrepancy. But I would rather think the opposite. I would say, well, actually, that would be the occasion to try to make that link. But the results have been rather inconsistent so far. So in some studies, we had kind of detrimental effects of doing that, of using like anatomical graph on functional MRI signals, like some of the things that Miriam has done. And in some of the studies, like the one I showed earlier from Abdel Brahim, we showed actually some very significant boosts. So we showed that we were able to restore some information that was lost using the anatomical graph, even though actually it was not even a graph from the same people. It was like an average, actually it was your graph, like the graph from the study with Julia Preti. So we showed that using this graph, we were able to restore some information from the functional MRI signal in the ABITE dataset. But that's why I say I think the results are still a bit inconsistent. We're not very sure. And what we're currently doing is more trying to combine modalities which are far more different, which is EEG and MRI graphs. So this is a bit more challenging because of like source localization issues, but we have current ongoing work from Venkatesh that's promising in this direction. So, I mean, it's as hard to try to reconcile these things that it is in the network neuroscience field as well, that people already struggle in agreeing in which network makes more sense than another, which measure is more meaningful than another. I mean, we can discuss with Sophie as well about all the statistical biases that exist in this field and all the controls or the null models that are necessary. And yeah, there's still a lot to be discovered. And one thing that I think, then one recent idea that I've not seen very developed that I just want to mention is that maybe we actually need also to reconsider what we use as signals in terms of maybe not using raw signals, but maybe thresholded signals, because the properties of the signals themselves are not very well conditioned if we use the full, like for example, an EEG signal might be too dense. It might be more meaningful to use a sparse signal, and that adds one more layer of complexity of choice that we have to decide upon.
Maybe if I can then I mean, as you said, there is a certain discrepancy between structural connectome and the functional signals on top of it, which, okay, we can discuss if it's good or less good. But then if you would go with the functional connectome to define the graph, isn't there kind of a, of course, in one way you could go to gradients and like in the Margulis sense, and you analyze the graph, right, in terms of the eigenvectors of the graph population. But if you would continue to use that in the graph signal processing sense, isn't there a circularity in the reasoning? Because you have the functional connectivity defining the graph to analyze the functional activity again.
Totally. It's totally circular. So the way that would make sense, in my opinion, would be to define the graph using resting state, like the gradients, and then use the gradients, so the eigenvectors, to decompose activity during tasks, for example. So I know that Daniel's done it. He's not published it, though. And we've done it as well. We've tried it as well. And the hope in doing that is that it has very, very high functional relevance because of the relevance of the gradients themselves. So that's why, I mean, we pitched this paper with Julia earlier last year to consider like graph Fourier basis of brain activity. That was the idea. Like, are connectivity gradients, can connectivity gradients be considered as a graph Fourier basis of brain activity? And you can still use functional MRI and functional MRI to do that. There's no problem, as long as, well, you consider activity on one sense and resting state connectivity on the other end. For example, in movie data, like analyzing like naturalistic movie watching data, that can make sense as well, because you might be able to detect like contributions of default mode network more salient than sensory contributions. For example, when people drift off or start to mind wander, that's some of the things. I think Jonathan Smallwood also does things in this direction.
Okay, yeah, I agree with that viewpoint, although there is a certain time scale aspect to consider, right? Because, I mean, if you go with the idea of using the functional connectome to define the graph, even if it's from resting state, as you propose, that itself is also changing at a certain time scale, whether it be days or months or years. So you have time scale changes in your graph signals and in your graph. And so that's where, if let's say,
yes,
both pieces of information are from functional nature, there is a
so
certain
here,
difficulty.
yeah, so here we need new models. So yeah, so there are a few things, of course. I mean, there's, of course, like the graph slapions that you've proposed. There are different approaches for dynamic connectivity. So far, I've never been really satisfied by, I mean, extensions of graph signal processing to dynamic graphs. I'm not sure exactly how to do. Also, I have like passionate discussions with my colleague Bastien Padlou about this, who's maybe in the room or not yet. And yeah, we thought about a few things, and so there is a joint graph Fourier transform, for example, that able to do that, which is essentially the Cartesian product between the graph and the temporal graph. But I don't see how to do this in a simple interpretable way so far. So this is still something that is a little bit on the back track, let's say. So far, we just do one graph for each time point, one signal for each time point, sorry. So we consider like temporal signals, and we kind of ignore the temporal dimension by just considering like multiply the temporal dimension as many times as we need. But yeah, that's a very clear limitation. I agree that's like one big chantier for the future, like construction work for the future as well.
The versatility of the GSP is, of course, its major advantage, but
yeah,
it's also a challenge.
Yeah.
So Mathieu, do you like me to continue, or maybe we come back in a second round?
Yes, I think you can, as you want.
Okay, or it's as you wish. Maybe
if
it's
someone want to continue on this subject specifically, yes. But if you have something to say, you can continue. You can continue. Yes.
Okay, so for the others, feel free to step in, and otherwise, but maybe I can put in another question on the deep learning. So you presented both work where you use deep learning for, let's say, feature extraction and classification. And then on the other hand, for more your future outlook, if I understood it well, you also like to use deep learning in a type of brain-inspired neural model, where perhaps, I guess, the purpose could be to learn about how the brain works as well.
Exactly.
So for you, are these two different research directions you will continue? Because I think you will have different constraints, of course, on how you design the neural networks and how you interpret them, which is more important for the latter case.
Yeah, so I think that's the very powerful thing with transfer learning, is that we already have like lots of models that have been proposed and that have already been trained, that have excellent performances on very, very challenging benchmarks, like recognizing 500 different types of sound at the same time, like audio sets. And I think there's no need to try to necessarily retrain things from scratch, but we can just use these models. And that what makes deep learning very interesting is that it was not easily possible with classical machine learning, is that we can take the network and maybe reuse at a certain point at any temporal resolution, we can plug out and try to predict something else. So people started to do encoding models of brain activity with deep learning relatively recently. And I think we're the first one who are doing a very, very accurate model of auditory brain activity using this kind of techniques. And where this is going, I think, maybe I can just share my screen again for a second. Just going to show a few results we're having with this. Yeah, so just to show the kind of things we're currently doing, when using fine-tuning, we show that we actually have very, very significant boosts in how to predict brain activity. So this is quite interesting because without fine-tuning, we just take like a pre-trained network and we're able to just fit one more convolution layer to predict the bold signal, so the fMRI signal. That's the top picture here, like the no FT on the bottom or the top left part. And we show that actually the auditory regions in the brain are very accurately predicted, like up to 0.4 correlation, which is quite good for brain data. And if we fine-tune the network, so if we go back into the deeper layers, we can actually have very significant boosts and also start to predict other areas in the brain, like visual areas significantly, as well as inferior frontal areas. So this is quite interesting because we show that from a model which was initially trained to recognize sound, we can actually predict brain activity in the auditory cortex, but also in other parts of the brain, which are related to maybe interactions between vision and audio, as well as language-related areas, sorry. And the other thing we're doing with this is we are using the fine-tuned model to try to generalize to other tasks. And we've shown that actually, so we are using a benchmark of many other, many deep learning tasks based on audio, which is called the HEAR benchmark. And we've shown actually that we have consistent average gains in with fine-tuning when we actually use brain data to fine-tune the network. So this is quite intriguing because this is kind of a way that shows that brain, as you said, like neuroinspired, like not really neuroinspired, but more like fitting brain data to fine-tune the network may boost performance on certain audio intelligence tasks, so which is artificial intelligence tasks. So I'm not saying this is going to necessarily, be very important gains, but the relative gains are very clear. In average, we do that on several subjects and on many tasks. So this is one direction I see as quite promising.
Yeah, it's very exciting how these neural networks also can be used in many different ways. It's especially in neuroscience. Okay, so maybe I give the opportunity to somebody else now, and I could continue also afterwards.
Okay, Peter, if you want to continue. Peter, do you want to continue?
That's fine. I can ask you a couple of questions, Nicolas. First of all, I would, of course, like to reiterate how wonderful it was to read your, it's not a thesis, I don't know what you would call it, but your summary of what you have been doing over the last 15, 20 years. And of course, I've followed it also a little bit from the side. And I think that it's very clear from my point of view that we need your kind of people in the field, as has been said before, because this cross-disciplinarity that you have already, I mean, you being a musician, obviously, but then so technically skilled. I mean, I would hire you immediately if I had that opportunity, of course, because see, it's really rare that you come across people like you that can also like both understand what are you investigating and how to investigate that. And clearly also one thing that I think hasn't really been said yet is how pedagogic you are. I mean, this presentation was really pedagogic, even though there are some pretty difficult things to understand, even for a mathematician such as myself. But this is maybe also so there's, I mean, there's nothing in what I'm going to say from now on that is going to take that away, and this is just to maybe to push you a little bit on a couple of things, because what typically happens to people like you, I've had several, and that is that you are so good technically that you end up participating on all people's different projects. And that's maybe also why you started out by saying there's a little bit of, I recall what you said exactly, but that this is, if you should summarize, it was about sound, which is kind of a big big label to put on everything. So the thing I would start by asking you was, I mean, it's really the classic question, and that is, what is really your project? What is that you really want? Because I could easily see you end up with a big center, such as, for instance, the Center for Music in the Brain in Denmark, or something like that. But that would probably mean that you would have to have some kind of more clear goal, at least for other people to see. So if I gave you half of my grant, let's say, all the resources that you could spend basically for some years, what would you really spend them on solving? Which question would you spend them on solving?
Okay, so I think I would really like to contribute to a better ecological understanding of auditory neuroscience. So trying to understand auditory cognitive neuroscience of humans, or maybe other species, but let's stick with humans for now, of humans under natural situations, under habitats, like how we are in daily life. And I think by doing that, we can actually learn a lot on how to build better artificial intelligence systems as well, because the way AI, deep learning and all that is currently being done is using very, like standard curated data sets, which are large, but which are still relatively controlled and relatively balanced and like with statistical properties. And I think also for the AI field, we need more ecological settings. We need more like real world data and things that are able to be dealt with in a real life kind of fashion. So my core interest is auditory neuroscience, auditory cognitive neuroscience, and we need to be able to do ecological studies. We need machine learning. We need this kind of methods to be able to disentangle the complexity.
Okay, sorry.
Yes, go ahead.
That's super good. Because one of the things that I saw, one of the many projects on your side is maybe a place where you could help us understand exactly how this could, how the deep learning and machine learning approaches could help us. For instance, if you look at your improvisation, musical improvisation, that is a really hard task to study using normal methods because improvisation is basically so many different things at the same time. So could you just, for the naive, a completely naive person like me, help me understand what is it then that you could use machine learning to do in such a setting?
Yeah, so I guess one has to find the right combination between how to document the task, what is being done by the subject, and try to use ecological settings and machine learning to generalize to the diversity of what the subject does. So in terms of the improvisation study, I talk about it in the manuscript. I unfortunately don't have the slides here to talk about it. What we've done is that we've asked the improviser to do mental retrospection of like his thoughts while he was playing. And we try to quantify that by having like a measure of flow state during improvisation and a measure of like time perception, like more subjective temporal perception in terms of how fast or slow he was kind of thinking. And we've used machine learning afterwards to try to link the retrospective ratings with EEG data during the playing. And I think this kind of paradigm, I wanted to decline it. So I mean, to be provocative, I would tell you like I wanted to write an ERC on it. It's not exactly that, but I mean, I almost did it. But that's the idea, you know, like to try to document daily life in a way by using as much description as we can, and to ping back on your question on why machine learning. Well, I don't know if you've seen these very recent models that are able to generate photorealistic images using text. So it's very impressive. It's coming out of the news now, like we can see it a lot. And some people start to say one of the limiting progress of machine learning is the availability of language supervision. Like as soon as we have, like we now have very, very large language models, which are able to do very complex things with language, with natural language understanding. So imagine if you had a complete description of the state of mind of an improviser when he was playing, time locked to the moment he was playing, you could almost try to recreate kind of like a musical flow related to what he describes a posteriori, which would be like a kind of an ecological description of what he's doing. And this is where maybe like this more like in the 5 years or 10 years application thing I'm talking about. But just to give you starting points, things we couldn't imagine like 5 years ago start to be possible today with this kind of progresses in deep statistics, I would say.
Yeah, but I mean, I completely follow since we have just done this, but we haven't published it yet. That's why I also am asking you. But we used kind of we used kind of a different method. You probably have heard about the leading eigenvector dynamical analysis by Joana Cabral and so forth, and we used that on our improvisation data. And of course, what you can say, and you might have a good. The good thing about this is if you're thinking about an improviser who is improvising for 30 seconds, then he would probably be shifting between different brain states along the way. And that would be different from the other one that you also would need, because you would probably need a lot of subjects to be doing this. So that's why these kind of methods are much better suited than because you can't control, basically you can't control what is happening, but you might be able to actually extract it using these things. The problem in what I've seen here, or in what we have been doing, is of course that when you use these, you build these models of brain connectivity, right? And here you need to take a lot of assumptions. When you do it, for instance, you need to figure out how many states will you actually allow there to be, because you could have 1 billion states, to one to each, like the postulation that Dimitri was talking about before, right? So the problem here was the k-means clustering. That is hard to it's hard to sort of say it's exactly this k, because if you change it from 4 to 6 states, then you might get completely different things. And how far are you with this kind of figuring out what could be the state of the art? Because there's so many different approaches, right? So what would you say about the field? So what would you say about the field? Is there some kind of consensus coming up on this, or?
I don't think there is a consensus coming up. I mean, I think there's no free lunch, as we say, right? I mean, there's no one size fits all. So it will really depend on the research question. I mean, in the improvisation study, we turned out that, I mean, it helps quantifying what you can quantify. It's, I think, safe to do some choices at some point to say, okay, maybe we just have 2 states of temporal perception. That's what we done. Like we had the HMM and we fit it with 2 states. That was a binary descriptor. And then we use this binary descriptor as supervision for machine learning, trying to see if we can predict one part of the data using the other part. Yeah. And that gave satisfactory results. So we went with that and interpreted that. I think it will really depend on the question. There's no, I don't see an universal answer. But I mean, the thing I see though is that there's like, again, transfer learning, because for example, there's like Martin Rohrmeyer recently pushed a model to predict harmony using, okay, so it's on symbolic data though, but it's on you need like a MIDI file. But if you have a transcription, you could have like a running harmonic prediction of what's coming up next. Okay, but the exciting thing to do, the step above, the step after that, I think, is not use the output of the model, but use the internal of the model. So I know that, for example, one of the PhD students of Luc Arnal, with whom I'm collaborating with, he's doing that for musical prediction. So like similar things than the idiom model, but with like a deep learning model, and using the intermediate representations to see whether you can predict what's coming up next. And I think that makes a big difference from using like k-means or eigenvector decomposition methods, because these models have already been trained to do something, you know, so they are adapted for a certain purpose. So you can consider them as a, you know, an organism in themselves and have their own, you know, activation patterns that can be reinterpreted in another way. And I think personally that it's more promising to use multiple models trained for other purposes to interpret experimental data rather than trying to retrain things from scratch.
Yeah, I'm with you on that. So, but some of the things you have been looking at, and now I'm just asking. I know this is not necessarily simple, but it seems as if some of it would be good to look at with intracranial recordings, for instance, to make sure that you know, I mean, so that you actually have a better idea of the exact network and what is coming from where, because all our methods, e.g., even MEG, is kind of you're pretty far away from the sources, and of course also animal studies would be something. Do you have any plans on going or collaborating or collaborations even with people who are doing this? I know that the Marseille group of course works with this. And
so I discussed a little bit with the Marseille group, with Benjamin Mourillon. Yeah. And also told me that he has a contact, I forgot her name, but she has lots of fMRI EEG simultaneous recordings. But yeah, no, even for each cranial, I think they are really trying to deploy that. They're talking about having lots of music perception. So yeah, that might be a plan for the future. But you're right that, yeah, I've never touched it yet at all. But yeah.
No, I'm just saying that I think your expertise would be very welcome in that, in those studies, and I would really encourage you to talk more to Benjamin or
Right.
I mean, we are working together with Bob Knight in California. I have a postdoc over there at the moment, and it's really exciting. The problem, of course, is that you need a lot of subjects, so you need to find a place where they do have a lot of subjects. I mean, intracranial recordings is only for people with the epilepsy, of course.
Yes, of course. Yeah.
But yeah, so just to go, so if I may, I'll just go a little bit more on some of the more specific things, because now we haven't talked about your also exciting stuff about Parkinson and earworms and all that. So I would just like to shift a little bit over to that, if that's okay with the panel. I know that your future is probably in machine learning and deep learning stuff and graph theory, but I still think that, and even though I know you have been sort of employed on some of these projects, then so they might not be your I mean, so close to your heart as the other things. I think they're really, really interesting, and I think that's. I do think that I do believe that Parkinson's patients is one of the best clinical applications of music because of this specific thing that that humans and not animals actually move to music. So I would like to, if you look at your Parkinson stuff, very simply, what would be the most important take-home messages from the work that you have been doing in this, and how could that be applied in a way?
So I didn't mention it in the defense, but I mentioned it a little bit in the manuscript. So the second paper that we've published, and first author is Simone Della Bella, we showed that there might be some predictors of therapy. And I think that's the most important thing we're looking at. That we're looking for that, right? I mean, ideally, we would like science to be able to give these kind of answers. So investigate individual differences. Like patients all have a different response. Some of them respond very positively, some of them respond not so much, and some of them respond a little bit negatively. So we've shown that the way patients spontaneously synchronize their steps to the music was actually maybe indicative of how well they would be rehabilitate. So that's very promising. And actually for that specific reason, I think there was a lot of activities that were launched after this project that was in collaboration with, so I know that Simone has set up a collaboration with a startup in Montpellier that is called Natural Labs, and now that he's back in Montreal, I think he plans to continue like doing these studies with Parkinson, with the Basta and the same things. So I've not followed up that much on whether that is going to make a difference. But I think the critical limiting factor was that the effect of therapy was washing off after some time. So we have no idea. We have no idea why, and we have no idea what to do.
No, I mean that, but in a way, I mean, Parkinson is a genetic. I can't say it, but it goes down. I mean, it doesn't become better over time. No. That's how Parkinson is, right? It degenerates, or the people degenerate, right? So of course it will wear out, but I think you might use music, of course, to because people are motivated by music, and so if you could have them doing some kind of therapy that they could do themselves, that might be a future.
So I think you remember probably Charles-Étienne Benoit. So I think he's been trying to do that. He's been trying to have an app that people can use with natural piano. I think Simone and Charles-Étienne had some kind of things like this in mind. I don't know whether that ended up being a product.
But actually, I would like to ask you, because wouldn't it be, now you're saying it would be good to sort of have a diagnostics of who would benefit from musical training, for instance.
Yeah.
And could you actually use brain scannings to do that, and maybe even kind of classification, some kind of classification of that?
Yeah, we had preliminary data that was in a subset of 10 patients that showed like a correlation. I don't know how strong that was, but between like connectivity between the basal ganglia and supplementary motor area.
Yeah.
That was correlated with the success of therapy. So that was quite promising. There was just 10 subjects and with like very noisy fMRI resting state, so we never published it. But but yeah, I mean, still there might be something, and I don't think anybody has done it. I don't know of any open recent data set of, I mean, just like gold MSI, like musical training measures with resting state fMRI on Parkinson would already be something interesting to look at.
Yeah.
I'm not aware of such a data set, and then I mean there were reasons to think that there may be some like structural and functional connectivity correlates with the therapy as well, like with predictors of therapy outcomes only in the connectivity data. We actually seeded the dentate nucleus of the cerebellum, the SMA, and there were like a few correlation patterns, but again, this is something that was weak and noisy, so we were not very sure.
Yeah, because you can say that the problem with Parkinson patients, of course, if you scan them, you have to have them, they have to lie still in the scanner, right? Which is already difficult. They might be on medication, which would also change the functional connectivity if you do that.
Indeed.
It's not an easy task, but I think for the future, this would be an important thing to try to do, but it would take it's a tough job to do. But that would also be an ERC possibility, of course.
No, but I mean, maybe we'll have the opportunity to talk about it with Serge in a minute. But I mean, the local university collaborations would more able like large cohorts of stroke patients, and there might be more opportunity in this direction for us in the near future. So not necessarily with music therapy, but more with like the brain network analysis and things like this. But then, of course, I mean, internationally, if there would be possibilities to work again on Parkinson, I would potentially be interested in at least being involved in setting up things.
And then I would just, if I'll just touch upon the earworm, your earworm studies with Lawrence Stewart, of course. If you think on those studies, what were the challenges by doing this? Because this is, of course, something that if you give a public lecture, there's a 90% chance that somebody is going to ask you even though you haven't talked about it, what happens to the brain when you get a tune in your head? So what are the actual challenges? Why what and yeah so
we've spent some time thinking about how to even find a paradigm to measure it, and it's impossible. I mean, it's not impossible, but I mean, okay, so you want it to be involuntary, so you want it to happen spontaneously. So you're not going to put someone in an fMRI scanner and wait for him to have inworms. So there are some priming paradigms or related that have been done behaviorally. My colleague Georgina Floridou has done studies like this, and as well as Beeman has published a few paradigms in which like you give, like there is like a pretext musical stimulus going on for some reason, and then there is another task done in silence, which is a boring task, and actually the musical stimulus was a prime so that people get an earworm from it, but you don't ask them until the very end of the experiment. So you can do things like this, but we never really agreed on a way to do that reliably, even to do an EEG experiment. I think Rebecca Schaefer with Georgina, I think they've tried to do an experiment like this, but it doesn't. I don't think it has worked. But we don't really know. The thing we know is that I was collaborating with Jonathan Smallwood, who's a researcher in mind wandering and is interested in self-generated thoughts. And that opened my mind quite a lot, actually. I think that opened a completely new avenue of cognitive neuroscience. And this is also still part of my thinking. And they are able to detect when people might wander in the fMRI scanner. And also there are some markers in EEG, and as well as pupil dilation, like using oculometry. So they're able to know when people become off task, essentially. So you have a task, then it's boring for some reason. People start to drift off, think about something else, and we start to have some hints about what the brain does when this happens. So we talk about couplings between the default mode network and other systems that kick in and that kind of shut down the sensory contributions. So I have a working model of how earworms might work, you know, based on this kind of ideas, like interactions between default mode network areas and auditory areas that would go fetch some long-term memories, trigger a loop. But I mean, this kind of quite hard to test with current situation, but that was kind of a little bit of a motivation to also study decoding and machine learning to be able to maybe one day decode that. But we will need a paradigm in which people do have it. And this is still the problem.
I know. So I think I'll conclude my part here. I'll just say that I think it's so important that there are people out there trying with the ecological paradigms. For myself, I think it's important to have sort of both very controlled and very ecological approaches that can be combined.
Mhm.
And I completely agree with you that like these whole brain computational models and so forth, they are the way to go in order to study the ecology, because so many things differ when you start looking at ecological paradigms. But I'll leave the floor to somebody else. I'm really happy about what you have shown here.
Thank you, Peter.
Thank you. Geoffroy, do you want to continue?
Yes, do you hear me?
Yeah.
Okay, great. So congratulations, Nicolas. Congratulations for your work. So I think we are actually colleagues because you're also from telecom, but you
Yeah.
you're from Britain. And we nearly meet each other because I was teaching audio up to one time at NCA in Cergy-Pontoise, but I
Really?
think that was after you finish your studies. But I mean, I nearly was your teacher of audio and music information retrieval.
Right.
Yeah, so thanks a lot for inviting me. I mean, I learned many things, and I was really impressed by reading your manuscript. I mean, it's really multidisciplinary. It's really impressive because you touch so many different fields with great skills that it's not only multidisciplinary in the sense that uh, you study very many different things, but also you succeed to combine them. So that was a real pleasure to read it. Even if I'm not a specialist of many of these fields, so I think I'm mostly here concerning music, audio, and deep learning. But it was really interesting to see everything related to cognitive neuroscience and all the experiments you did. So really, congratulations for that. It's a very good work, and also something which was not mentioned is that so far is that I mean the way you create your teaching program is also really interesting, and it's really novel. That's not really common, this kind of topics. I mean the one on the specific deep learning program on reducing the size of neural network. I think it's really good to have to create this kind of program. I
Thank you.
wish you will have I wish you will have the same in at Telecom Paris.
We are very proud of it.
Yeah, you could. Probably we will invite you so, since we're colleague. Okay, so some comments. So I will try to be brief on this. So everything you did is really it is really interesting, probably just on a very generic level. The the thing which I realized after that is that the first part of your report mostly deals um, uh, with temporal signal actually. So you have all the analysis on the synchronization um, of beats uh, with the self-paced, paced and continuation, which is really interesting. All the gait prediction for Parkinson disease. But in terms of deep learning models, that's mostly in the second part of your PhD, where you deal mostly with the spatial aspect of deep learning with the graph neural network. And I was wondering why you change. I mean, except that the topics are not the same, but the first part is mainly about the temporal modeling, and then you have this hidden Markov model with multivariate autoregressive, but which is not which is linear. Is not a non-linear model, which is actually the main thing of deep learning is that it's non-linear. And then the other part is about graph neural network. And why did you suddenly change why did you decide to change the point of view and then to study the spatial distribution of the data rather than their temporal evolution?
Thank you, Geoffroy, for this question. It's a very, very, very good point. Yeah, so it's actually related to an earlier point from Dimitri that we talked about the temporal dimension in graph signal processing that is missing. So yeah, why did we switch? Well, I mean, when I came to be completely honest, when I came to Telecom Bretagne first as a postdoc, when I got my position as an associate professor, graph signal processing was like emerging theme in the group. So there was back in the day, Bastien Padlou was doing his PhD, and he was the one working on it. And we first tried we hired a postdoc to replace my former postdoc when I got the position, and we wanted to test the idea of graph signal processing for neuroimaging. And there was absolutely no temporal dimension anymore. There was more like the whole team was built on the idea of exploiting graphs in machine learning. And I came with an expertise in neuroscience. So that came as like, the combination. So what you are asking for is something that I'm trying to build progressively, actually, which is to try to integrate again the temporal dimension in what we do with graph neural networks or graph signal processing. So we are starting to do it now. So there was no specific reason for not doing it earlier, just more like serendipity. Just like the fact that there was a motivation to do it because of the forces in place. And we are starting to do it now in the PhD thesis of Venkatesh Subramani, in which we look at temporal signals, which are brain activity during movie watching. So people who are watching the same movie, 25 subjects. And we are using graphs for spatial dimension, and we are exploiting the temporal dimension more like in a classical frequency analysis, like Fourier analysis, and we divide the EEG signal into specific frequency bands. So the mixing of the both is quite complicated because we don't have a unifying model. We mentioned that with Dimitri a bit earlier in the discussion. It's difficult to have a really convincing unifying model that is interpretable and tractable to my understanding, to my knowledge so far. And just working with one dimension and expanding the other one, so to say, is currently easier than trying to have a unifying model that exploits both spatial and temporal dimension. So yeah, I guess the motivation for switching and also for not doing both is reductionism somehow a little bit, and also like opportunities like regarding like what was being done in the group when I joined and what I like progressively developed. But yeah, I think we should do it definitely.
Okay, because I guess that most of the information that you locate in the various parts of the brain are not activated jointly. And then you have specific temporal path of activation between the various cells in the brain, and that you could get some information there.
Yeah.
Yeah. Okay. So, yeah, but I don't know what are the status in a graph neural network, if it includes some recurrent neural network in the connection, or if that's some still in the.
Well, the thing is, we can use graph neural networks to deal with the spatial dimension, but then we can use like one-dimensional convolutions to deal with the temporal dimension. Like a single
Okay.
model can do both. It's just that
Okay.
well, I mean, one way that we've done that was with a collaboration with Pierre Bellec, a paper that was just published. I can show the slide. I have a backup slide on that. But it's a very, very basic way to use the temporal information. Okay. Oh, that's the one. So yeah. So the thing is, in that case, we use a Chebyshev network, which is a way to define graph convolutions using Chebyshev polynomials. And it's fMRI data, so it's temporal signals. And the way they get into the network is simply by considering as many input channels as temporal points. So that's a very, very basic way to combine the temporal dimension. And as soon as the second layer, you don't have any temporal dimension anymore because it's been combined.
Okay.
So that's a very straightforward way, but it's very efficient.
But each neuron doesn't really have a memory. It's
no, there's no.
Okay.
Yeah, you learn dependencies between the t time points, and that's it. Like for each trial, because like this is not dealing with continuous time. This is dealing with like trials which are like all of the same size, like 10. It's fMRI, so it's very slow. So we like 30 seconds of data is like just 10, 20 time points.
Okay. Then it's I was really interested in what you did with SunNet in the Neuromod project. It's kind of a self-supervised ID where, so if my understanding is correct, you basically training a neural network to predict fMRI signals from the output of SunNet, from the likelihood of the class. Okay.
Yeah. No, not from the output of SunNet, from the previous layer. So from
the previous layers.
Yeah,
okay.
from the like
from feature
not
representation.
not the output probabilities, but just the layer just before that, the embedding that is before.
Okay. And then my question, is there any specific reason for using SunNet to do that? Or
So yes and no. So the thing is, this project started quite a long time ago. I did the first experiments for brain encoding using SoundNet. It was in 2017, and back then SoundNet was more popular than today, and also more state of the art.
Yeah.
But there is another reason. The other reason is that SoundNet itself is trained on visual audio correspondence, because it was trained using visual distillation, like distillation from visual networks. And I think it's really interesting because it kind of encompasses the links between vision and audio. And we thought that would be a good way to encode what happens in the brain of people watching films. Because and actually I showed earlier a slide in which we see good predictions of auditory regions, but we also see good predictions of visual regions, which might come from the fact that we use SoundNet, and we might not get that from another network.
Okay, yeah, but that was my point actually, is that I mean, the fact that you succeed to predict the vision in the brain from the sound is actually due to the fact that SoundNet actually does the distillation from the vision output of the network. So whatever there is the sound corresponding to audio, there is the sound corresponding to an object or a scene, he will try to represent it as an output. So they could be also, it could be a gain, but also a bias, because that means that the information is not necessarily in the sound. That's interesting. Then I also like the part, when you try to create lightweight network using 1D convolution for the decays challenge. And you use 1D convolution, then you have a very I think it's interesting, but I wanted, when I read that in the report, I mean, it was a bit strange because you use actually something which is really meaningless in the physical sense to do a 1D convolution on the audio waveform. And it's kind of really contradictory to the rest of the PhD, where you want to carefully understand all the part of the brain, and then you put the 1D convolution on the waveform. So, I understand that here the point of view was not to make any semantic interpretation of the network, it was just to have a lightweight one. And can you comment a bit on that? Because it was surprising.
Totally. Yeah. So I like the challenge. So you're absolutely right. That okay. So I'm completely aware of the fact that most, you know, it makes of course a lot of sense to use cochleograms or like Mel spectrograms or like things that represents the human ear perception a bit better. The motivation in using 1D convolutions was actually to keep the waveforms. So to not go in the time frequency domain. So the alternative would be to use the time frequency domain, but not drop the phase. And I guess that's also one thing that should be tested properly at some point, because most of the time, so the thing that the starting point of this work is that I found it weird that the state of the art in deep learning for audio was spectrograms, then vision networks, because essentially that was what I was able to see back then. So there are some waveform networks now that works, and also like spectral transformers based on waveforms and stuff like that. But most of the time, I was not satisfied with this idea of just considering the problem as a 2D problem, because I don't think you have invariance. You have like 2D convolutions learned on a spectrogram are a bit weird because the kernels are not like, you don't have X and Y translation invariance, because Y is the frequency, X is the time. So, you know, I thought that, okay, let's just see how far we can get just with the waveform and 1D convolutions. And yeah, the brain does time frequency transformation right like early on. We know that, but it also preserves some aspect of the phase information. So there's also other things that are transmitted, not just the spectral, not just the time frequency representation. And it's still not very clear how. SoundNet is 1D convolution based model, by the way. So that's also why.
Okay. I mean, there are many reasons to use 1D representation or 2D representation. One of the gain of using 1D representation is that, of course, you have the phase if you use the waveform, which you avoid when you use the mailgram or the spectrogram. But there has been a proposal to use the complex spectrogram as 2D representation. And also, most of the time, you end up, when you train 1D filters, you end up having some kind of bandpass filters, gamma tone. Then that means that introducing the bias that you're looking for some frequency representation from your 1D filters actually help. The thing, and you're completely right, is that a spectrogram is not an image. So doing this convolution over time and frequency with spectral invariance doesn't make sense. But there has been also a lot of proposal of changing the shape of the filters, such as Vincent Le Stanlen has proposed to have this source filters model in the 2D convolution to somehow make this invariance. So what I mean by that is that, and that's also related to the perspective at the end of your report when you're trying to define inductive bias for auditory cognitive neuroscience, and there is currently a large literature on finding what is the right front end to process audio signal. Including preserving the phase. So, for example, at École Nationale Supérieure, there is the group of Rachid Riyad, who is doing all the spectro-temporal receptive fields in a differential way. Because the current trend in deep learning for audio is to reused all the models we know from auditory perception, such as the gamma tone, the modulation in time and frequency, and to make them differentiable. And that's the trend since Ravadeli with the SyncNet is to do differentiable signal processing. And that's a very convincing way to introduce signal processing while preserving, because in your work you preserve the spatial decoding in the brain, but then there is really the process in the here, and this decomposition as modulation. So I recommend really looking at the work of Yannis, which is really valuable.
Definitely.
And
Thank you. I've
and
actually
then
seen, that's one paper I've presented quickly this week in the lecture group we have is from Riyadh, group from Riyadh, the Deep Stride work that was published in iClear last year. Yeah.
So that was the paper he published this year, and last year he had very nice papers on learning spectro-temporal representation.
Mm-hmm.
And yeah, to finish, I was really intrigued about your project about joining the EAR NeurIPS challenge. How do you think you could really use the thing you do with the work on SunNet? Because in SunNet you did somehow the opposite. So that means you tried to predict the fMRI to from the output of SunNet. So do you think that just training this way could lead to a good neural network that could be a good pre-training for a universal kind of
yeah. What we have currently in this direction is that we just wanted to test the idea of what happens after fine-tuning using the brain data.
Mm-hmm.
If we reuse the embeddings from the fine-tuned SunNet, how does it evaluate on the HERE benchmark? So we've run the HERE benchmark on many repetitions of like SunNet, just not fine-tuned. And we've also took all our fine-tuned brain models. And what happens currently is that we have absolute, relatively like not good performance in terms of like we are in the third part of the leaderboard, let's say, like the last third. But with fine-tuning, we consistently have gains which like make us take like 1 or 2, 3, 4 steps sometimes. In terms of relative gains, the largest gains we have is 20% gains, like 20% relative to the baseline, and the baseline instead is not good. So for example, if you have I can show the slide again. This is really fresh, something we're really just currently doing, but I find it really exciting, so I'm happy to talk about it.
I'm excited too.
Yeah. So let me open my slide set again. Yeah, no, this is really quite exciting application. So, c'est pas le bon. Comment c'est Evans qu'il faut que j'ouvre. There you go. Tac. Application, fenêtre. Voilà. Hop. Yeah, that's the one. So if you can see, for example, for FSD50K, you probably know, we have like a 5% improvement relative to the baseline, but the baseline is like a mean average precision of 0.18, I think, which is quite bad for FSD50K because like SOTA is like 0.54 something, and you know. But we have other tasks. We have like, and the pitch tasks are quite not so bad. I don't remember the absolute, but like we have up to 20% gain. And what's funny is that it works better if we fine tune using auditory brain networks and not the whole brain, which is indicative that maybe actually like auditory area, superior-temporal gyrus voxels lead to higher gains than using fine-tuning of the whole brain.
Okay.
So this is like
then
work in progress. But yeah,
So that means that in this case, you only fine-tune the network to predict the auditory areas.
exactly.
Okay, so that's only the fMRI signal from the auditory area.
Yeah, bilateral
Okay.
auditory cortices. Yeah.
Okay. So then it keep any visual
Yeah.
part.
Yeah, we've done
Yeah.
both. Like we've done whole brain and just auditory.
Okay.
So that's quite exciting. This is work in progress.
Yeah.
So on ESC50, we have like I think the absolute performance is 40%, which is also quite bad for ESC50. And we don't know if it just comes to maybe taking a better baseline, or if there's something else. If we would take a network that would be already state of the art on ESC50, fine-tuned with brain data, would it lead to better, or would it peak performance? I don't know. This is like completely new, so we don't know.
Okay. Thanks a lot. I will let the floor to my colleague. So congratulations again, Nicolas. So this is your work is fascinating.
Thank you.
Thank you. Sophie, it's your turn.
Thanks. Can you hear me? It's okay?
Yes.
So I was not able to control the camera, so I'm still blurred. Sorry.
Blurry Sophie.
So I will join my colleagues to congratulate you, because I'm always thinking that it's very nice to make the link between the methods and the real data, and it's not easy, as we all know. And I may ask you some question about this aspect, actually, because maybe the first one would be same sort of question as Dimitri about the deep learning in terms of the use of the data, because we all know, especially dealing with pathology, that it will be very hard to get a high number of data sets. So what's your comment about that?
You mean having large amounts of data for like temporal data with graphs, or I'm not sure I got it.
I'm thinking more about deep learning, the compromise you have to get robust classification. And in neuroscience, usually we are facing the lack of data sets.
Yeah, so there's two aspects. First, I think we are soon getting to a point in which transfer learning is going to start to work on neuroimaging data, because we have we start to have very large scale data sets of for brain decoding. So at least for brain activation maps.
Yes.
When you consider first like human connectome project datasets such as individual brain charting from INRIA, and Neuromod, the Neuromod dataset that is now just available, by the way, with very dense sampling of 6 subjects, 500 hours per subject. This starts to be an amount of data for which you can train backbones and attempt generalization to other things. So we are currently testing these kind of ideas in future learning settings, with like in collaborations or with some of the students we have in the team. The challenge is more for EEG, I think, because the diversity in the data sets makes it extremely hard to build backbones and to have generalization across different data sets so far. So it's been the subject of a challenge at NeurIPS last year to understand transfer learning and generalization in brain-computer interfaces in EEG, and we've participated to that challenge. But it's extremely hard. So Yassine LYD is looking at this, is trying to see if we can train an efficient backbone and generalize to future tasks. But this is really the directions from the field that are currently very challenging. Also, some other people think it's possible. So a few days ago, Gael Varocco dropped this poster at OHBM. We said that pretty much he thinks himself that he will never solve it's impossible to solve the field because of too many problems in the field, including like culture problems in the way neuroscientists think about the problems, and the fact that quantitative data are always perceived as kind of a confirmatory but not as discovery. So there's also like deep problems in the way the research is being done in neuroscience, according to Gael at least. So I mean, there's a few controversies to try to tackle with, and I don't ambition to have an answer to to every of the single points, of course.
But I can understand you are more optimistic than Gael.
A little bit. It's okay. I mean, no offense for Gael. Of course, I totally understand this point though, because when I see the arguments, I mean, I can understand why this can be very frustrating. Maybe it's depends what the aim is, but I guess that maybe like in the publication, in like the editor, or like in different parts of what makes the field, there is a cultural habit which makes it difficult to advance certain ideas. Like people probably still see deep learning as a black box or machine learning as a black box and don't want to understand what we can use it for. And this is hard to change. So I think this is part of the like despair, so to say. So yeah, we will see. Like the coming years will be, I guess, quite informative in this respect.
So going on this question, what do you think is the most crucial next step in terms of developing this deep learning? So is it acquiring more data sets and maybe better in a sense, or working on the methodological part?
We have already, I mean, there's already quite a lot of data. There's been so much effort in the last couple of years with standardization, with the BIDS format, with Open Neuro, with like free access to lots of measurements. So, I mean, we could probably stop scanning. I mean, there's lots of new neuroscientific questions that need to be addressed, that you need new experiments. But for many things, when I see neuromod, I mean, I think, okay, I mean, we have like 6 brains, 500 hours. We have a large diversity of stimuli, large diversity of tasks. We can just spend the next 10 hours analyzing this data, 10 years, sorry. So, I mean, I wouldn't push for more data sets. I would be more inclined in understanding better why and how we do things. And again, I think transfer learning from other modalities like pre-trained image vision language networks can help a lot. As multimodal learning, I think is an avenue that can be exploited for this, for understanding all these neuroimaging data sets. And I would push for that.
Mm-hmm. And one different problem, I think, is tackling pathologies, where this time we don't have lots of data sets.
Nope.
And so what's your comment about that? And you try to work on Parkinson disease.
So here I think the key is the discussion with the disciplines, like with the different people involved, because it's not necessarily going to start with acquiring data. It can start with already getting to know each other between these different ways of doing science. So doctors have a completely different view, of course, of the problem, and we sometimes have opportunities to collaborate on data, but that does not have to be the starting point. I think the starting point should be to better know literature from both fields before embarking into trying to address this kind of issues. And I also think that the ecological approaches I'm advocating for probably have something to say here, because understanding like how to deal with patients is also understanding like situations of patients in under like daily under like their living circumstances, their living situations, living circumstances. So we might need to take into account this kind of ecological constraints to to understand it better. So yeah, the rarity of the data sets is of course a limiting factor, but I think we should not try absolutely to immediately apply all the progress to disease before actually knowing more about what's going on in this field.
Mhm.
So I would not be the first. I mean, yeah, I would not rush in this direction. I would say.
So, and maybe I would have some comment about the robustness of the results and how confident are we at the moment in all this machine learning, deep learning, graph signal processing? What would you advise?
We are not very confident, I think. Depends what you want to do. I mean, it really depends what you want to do. I mean, we do have benchmarks to test for robustness as well that are quite serious, but it really depends on the application. I mean, for diagnosis, of course, you need robustness, you need a very high sensitivity, you need to be specific enough as well. But we don't have ways to do adversarial attacks that are realistic in neuroscience. I don't see how this can be done without. I mean, what we can do is corrupt signals. We can work with the input, but we can't really. Okay, if you want to do an adversarial attack on an image, you can draw something on the image, or you can try to modify the image by trying to do some property, and that will change. That will attack the network. But you can also do that exactly the same way with any deep learning network by manipulating the input to see how the network behaves. So I would say as long as we are not trying to build systems that make people's lives depends upon, I mean, the robustness is not going to be such a critical factor, because if the goal is scientific discovery, anyway, we have to confirm the kind of things we find with deep learning with other means, with previous work, with other ways to look at the data, with other data sets, generalization. I think generalization to other data sets is probably going to be the key most of the time, I would say.
Mhm.
To new subjects, at least.
Maybe one question about in your manuscript.
Mm-hmm.
Let me find it back. I can't remember. It was on the prediction of musical training, I think. And
Right,
you were
yes.
talking about easy subjects and difficult subjects.
Oh, yes, that's not in the musical training part. I think it's in that's in the graph signal processing.
So this is a link again between datasets and methodological consideration.
So just to be sure, we're talking about.
It's page 42 from your manuscript.
Yes, yeah. Okay, so that's actually simulation data, the easy and difficult subjects.
Okay.
So that was done using a fMRI simulation. So that's like blobs, which are localized spatially at regions in which we know from previous studies that these regions are activated. And it's a synthetic fMRI model, which is like a mixture of Gaussians and a simulation of physiological noise. So that's why we run a lot of simulations, and some of them ended up being quite easy, some of them ended up being quite difficult. And we were able to show some gains some significant gains in the difficult case, which is interesting. Like graph sampling was more helpful when the simulations was in the more difficult scenario.
And so this is answering a bit your question about adversarial attack.
Oh yeah. Okay.
Because here you are able to simulate.
Yes, that's true.
On subjects.
That's true.
How far are the simulations from the real data? Can you quantify it?
No, well, that was really a very naive model. I mean, this is a model that was proposed. I can't remember the name, Physiostat or something. It's an R package.
Okay.
I don't think the goal is to really mimic true fMRI data.
Okay.
But the models that Pierre is trying to build and that we try to build with the auditory encoding models are models of brain activity. So that could maybe one day be used for testing the courses as well.
Okay. I was interested in these categories because in brain, as I understood, in brain-computer interface, there are also easy subject and difficult subject in terms of
In what?
In brain BCI.
In BCI, yeah, of course, yeah, definitely. Well, we currently see this with Yassine, in his thesis, that there's some EEG subjects which are extremely easy to decode.
Yes.
For brain-computer interface, and there are some subjects which are just impossible. You never get good performances, so you can reduce a little bit the variance, but you never like some subjects just have like very bad performance, and we don't really know why. It could be the signal, it could be the subject. We don't really know.
Yeah, that's strange. Yeah.
That's real data.
Yeah. Oops, I'm all black now. Sorry. I am in an intelligent building, and it's controlling the.
But how intelligent is it?
Yeah. I'm sorry. Yeah, I want to ask your last question about in your perspective. You're mentioning that it's worth having some back and forth experiments between cognitive and computational modeling. And I want to ask you, what do you think is the most difficult task in terms of, is it more difficult to build the correct cognitive experiment you want to deal with, or the methodological part?
I think it's extremely hard to find a good compromise between an ecological design for a cognitive experiment and a controlled experiment. I mean, we were discussing it briefly with Peter earlier.
Okay.
The best is to have a balance, like to have a ecological as close as possible to real life and a controlled stimuli experiment. I think it's possible to have a balance between both. So I guess the perfect paper would include like many variations of the same kind of paradigm, one very ecological, the other one very controlled, and maybe an intermediate version of it. This is things I would like to investigate in a middle term future, let's say, by trying to build upon wireless EEG or like new methods to measure physiological signals of brain activity. We are discussing with a team that does virtual reality for that reason as well at TMT Atlantic, to try to do like VR with EEG and try to bring a bit of like ecological validity in virtual environments with EEG at the same time with wireless EEG, which might enable us to do some, this kind of intermediate paradigms. Because the purely ecological paradigm would be to have like a subject out of the lab in the street with EEG, or like we've done with the, like in the Semaine du Cerveau, or with the Art and Science Festival. So like having subjects measured with EEG while watching a concert, in a real concert, like not in a lab. So I guess there's a huge project in Goldsmith currently going on, an ERC project, where they do that with dance performance, and they measure like 20 EEG at the same time on the audience. So this is the things that people are starting to do, stuff like that. And I mean, I've been thinking for a few years and doing this, but I realized that actually there's already research ongoing on this kind of direction of trying to put more ecological settings and out of the lab. So the balance is hard to find, but I mean, it has to be a consistent effort of testing experimental ideas.
Okay, thanks. Yeah, it's always very nice to discuss with Nicolas, and we spend hours discussing and interacting. But I will stop here. Thanks.
Thank you.
Thank you. And we finish with the clinician of the committee, Serge. We don't hear you.
I don't see you either.
Thank you, Nicolas, for inviting me.
Thank you, Serge.
participate to this journey. It is far from my background, and therefore it's quite stimulating, and I didn't understood all the different debate on the subject. I see that, of course, it is multidisciplinary, and I think it is very challenging to do that. But in the same time, I'm asking a little bit the same question as Peter asked. What is your fundamental question? And I think it's you have already started to answer to that. I'm not sure you have completely answered to this question. So do you have a comment on that, or?
So I'll try again. It's a bit hard, I have to say. No, but I mean, of course, I'm interested in many things, so I want to give multiple answers, but I try to keep it simple. So I'm interested in trying to figure out how the brain processes sound, the auditory neuroscience, in ecological settings, so in real life. So what that means is that the brain is able to perceive sound, but it's also able to imagine sound, to recreate sound. And we also have lots of internal processes at play, like predicting time, predicting when things are going to happen. And we think this might come from like subcortical structures, from basal ganglia and cerebellum that play a role in time perception. There's complex interplays between these different structures. I've shown that with my research in Parkinson disease, and I saw like there's multiple things. So ideally, if I was able to do so, I would like to combine these different things to understand sound and in its various dimensions, both perceived and imagined in the brain, in ecological settings, which means in real life, like in how we do it in everyday life. We sometimes have music in our head, we don't know why. And I think that can inspire artificial intelligence. I think that we can, if we understand this better, we might be able to build deep learning systems with biases that are inspired from the brain. That would be my answer.
Okay, quite understandable. Thank you very much. So my next question is, you said we have the ability to perceive temporal regularity. And my broader question is, how does it relate to time perception?
Okay, so typically time perception is divided into two subfields. There's like longer intervals. Like I think the boundaries is most of the time put at the seconds boundary, like several up to 5 seconds or 2 seconds is one mechanism. It's like from a few milliseconds to 2 seconds is one type of mechanism, and more than a few seconds is another type of mechanism. And it's not the same task, not the same result, and presumably not the same brain structures as well. I know more about the few hundred millisecond range, where it seems, so if you talk about time perception in the few hundred millisecond range, it's more like how does the brain react when there is like a slight change in the prediction of the next event. So you have a series of tones, for example, and they are isochronous, they are at the same interval, and then there is one tone that arrives a bit later or a bit earlier. That would be called an anisochrony. And that's what I refer to as temporal processing and like a deviance from temporal regularity. So that's this kind of mechanism that seem to be related to beat perception, that seem to involve the basal ganglia and especially the putamen, and that seem to be also impacted in Parkinson's disease, probably because of dopaminergic deep progressions.
Perfect. And my question is, do you think that these early events are playing a role in the long-term events? It means the time perception we could have, for example, in life, or do you think there is an effect on that?
So I don't know about it. I don't know of studies about it. I think from several seconds to several minutes, there's mechanisms that also relate quite a lot to working memory, so which is higher level. And if you go longer than that, which is like weeks, months, days, life, etc. Well, then of course you have the circadian clock, which is more on a 24-hour scale. And then I think it gets into long-term memory territory. So I'm not sure whether that can be. I mean, I'm not sure whether the time perception literature really considers it as the same kind of mechanisms to look at. But I don't really know about the links between the different scales. I don't think this has been investigated that much, to be honest. I'm not aware of anything that investigated this aspect.
Okay. I understand there is different models of time processing. There is it is said that there is a clock stage, a memory stage, and then a decision stage. And how your work is able to decipher this model, do you think it's true or not?
So actually, the work I've contributed to is not really relating on the pacemaker accumulator model or the memory model you mentioned. We identify more into the predictive coding theories. So Bayesian brain, more like the fact that the brain would continuously update the prediction of when and what the next event is going to be. And that would be the mechanism. There would not be a memory and a threshold with something that decides. And these kind of models are sometimes interpreted in terms of oscillations, of oscillatory models. So there would be like networks of coupled oscillators, which would actually compute the running prediction of when things are going to happen and what is going to happen. So it's still very hard to. So people have been relating that, for example, to the phase of the EEG. So when I showed the event-related potentials earlier with the modulations of the P50 and N100, in some of the experiments, I've tried to relate that to the pre-stimulus phase, because there's a lot of work, especially from Nathan Weiss on as well as I forgot the names right now, but people showed the pre-stimulus phase locking as predictive of the processing of the stimulus afterwards. So the ongoing oscillation of the EEG the phase would be predictive of how the stimulus is going to be processed. So that would advocate for an oscillatory model of time perception. So I guess the recent trends, I mean, since I started in neuroscience, of course, I mean, I'm relatively still quite new in the field. In the 2010s, at least, when I arrived at the MPI in Leipzig, everyone was getting into oscillations. That was like the dominant trend, so to say. But there's still a debate on whether there is oscillations at all, or is just evoked potential or evoked responses. So from the monkey studies, well, from the animal studies, I think there is some evidence from the pacemaker model, but I'm a bit far away from this literature right now to be sure of it.
Okay. You mentioned many times basal ganglia, the striatum, the caudate nucleus, and more, and the putamen. But the way you are studying this structure is not always, how to say, complete. For example, EEG is not analyzing the basal ganglia. So how do you think you could alleviate this problem, which is you have some tools which are not studying basal ganglia, but in the same time you are interested in basal ganglia because basal ganglia play a major role in time perception?
Yeah, so that's pretty much what we've tried to do with the Parkinson project, is that we know that we are tapping into basal ganglia territory because we are working with Parkinson's disease patients. Mm-hmm. And in the same group, when I was in the Max Planck with Sonia Kratz, a collaborator of mine, he had patients with basal ganglia lesions as well, and left side, if I remember correctly. So I was not collaborating on this project, but they had this pool of patients with basal ganglia lesions with the same EEG paradigm, exactly the same EEG oddball experiment that I showed. So that was that enabled to tap into the effect of having a damage to the basal ganglia on the EEG. But just behavior can be enough. in some way. If you're working with patients with lesions, and we are running the same task that I showed, the Basta tasks, what happens? Which kind of tasks are affected? Which kind of tasks are spared? That would be one way to go. Another way to go would be to use MRI, of course, functional MRI or structural MRI. So we started to do it, but it was too noisy to be exploitable. But we had some results on 11 patients, if I'm correct, where we showed correlations between structural functional connectivity between the dentate nucleus, so that's in the cerebellum, and putamen and supplementary motor area, which are, and the strength of connection was correlated with the success of therapy, which was
You mentioned that in your...
that was pretty promising, but that was, I mean, something we didn't pursue because of signal to noise ratio, which was quite low.
Okay. As you said, you are interested in Parkinson's disease, but in Parkinson's disease, in fact, there is a quite diffuse disease. It's not only basal ganglia. It's also involving the cortex and, of course, the brainstem. I was thinking, and you might be thinking of other disease, neurological disease, for whom we might have more localized lesion. Do you have a comment on that? I mean, it would complete work on
so
patients with Parkinson's disease, or?
So, I mean, there's this fascinating paper from Kuhl Cheng and Meck from 2011, Pharmacology something. It's summarizing all effects of time perception with pharmacological manipulations. So that gives a lot of hints of regions, or at least systems in terms of like neurotransmitters that are playing a role in time perception. So I've never done any pharmacological study, and that's, of course, obviously quite difficult to run today. But I mean, I see a movement, at least in healthy subjects, for standardization and data sharing initiatives. That exists for Parkinson, that exists for Alzheimer. That starts to exist a little bit for stroke to some respect, when I mean, with discussions we had about the large database you're building. But I don't see that for, I mean, focal damage. I mean, that could be included in stroke repositories, I guess. But I mean, that would mean, okay, we're interested in certain functions that we know certain focal lesions should have an impact on that. We will need to gather behavioral data on these people to have so that's pretty challenging, because most of the time we don't, I mean, unfortunately, these people are not there anymore, or, you know, don't want to bother people years after or anything. So this is moving too fast to be able to ask these questions properly without like an experimental paradigm that is decided in advance and run.
Okay. I wanted to add that your overview, your presentation was quite clear and very convincing. So it was nice for me to participate to that meeting, Julie. Yes. Thank you very much.
Thank you, Serge.
Thank you, Serge. Well, I'm the last one. I'll be quick. First, I agree with all the compliments that have been made, really. And I will have only one or two short questions. First, about the study on musical improvisation. The musician had to assess three factors, or two or three factors.
Two, actually.
Yes, the focus and the subjective temporal resolution.
Exactly.
Finally, you didn't keep the global quality.
No.
Yes. And you choose these factors with the musician, with one musician.
Yeah.
And probably another musicians would have chosen some other factors. And more globally, in this study, you observe the link between the subjective assessment and the electrophysiology measurement for one subject, and you published it. And my question as a psychoacoustician is, how can you conclude with one subject?
You can't.
Ah, okay.
You can just conclude. You can just conclude on this subject.
Yeah.
So I think it's, we're talking about improvisation. We're talking about something which is very personal and very idiosyncratic, but at the same time, it's also universal. So, there is a creative process at play, which is something that every musician has a different creative process. So the idea below this project was to document the creative process of one person and see how far we can get with trying to quantify a little bit. And the strength of it was to actually define what we do with the subject, which is not something that we do usually. I mean, you don't ask your subject, so what do you think would be important to measure? You don't do that. So it's a bit of a provocative statement, and it's also a provocative statement for ecological studies, and I think it joins with what we would refer to. So I really don't know how to say that in English. I'm sorry, but that would be like recherche-action or la recherche de terrain, in which this kind of research in which you go to document something in detail by actually including the object of interest into the design of the experiment itself. So people from humanities do that already. I mean, they want to, like sociologists do that. Okay, so this kind of actually this particular way of working comes from quite a popular person is you may know Bruno Latour. So it's his approach. It's trying to actually make research closer to not just research, but just like to try to include the beings that we want to help or understand or study, to have their point of view directly into the research question. So to give one more example, so that was an example of including the improviser into helping us define the interesting research question about improvisation, which makes the scientist, me, think about what is a good research question to study improvisation. And for him, it's also a way to introspect, to have introspection about what is the creative process and how can science help me understand my own creative process. And in the same range of ideas, in November, I'm going on in Ile de la Réunion with a collaborator to work on soundscapes with inhabitants from the cities. So we're going to actually organize a small workshop with the inhabitants to try to document the soundscapes, and actually the night soundscapes. So that's a way of doing research which includes, which is a closed loop, so to say. So you don't generalize, you don't make conclusions in the way that, a psychoacoustic researcher would with this is a 40-person group study or something, but you actually attempt at having this kind of humanities approach where you take into account the point of view of the other side and trying to work with that.
Okay.
That's a long, uncomplicated, convoluted answer, but I hope it does answer something.
Yes. Okay. About this study, I would be curious to see the brain activity if the musician had played the same notes, but without improvisation. I mean, if he had replayed exactly the same thing, but without improvisation.
So he would tell you it's not possible first.
It would?
He would tell you that it's not possible first. Christophe would tell you that.
Yes.
Musician, because he was not playing alone, he's never solo. So that would, and I don't know if you remember the kind of improvisation we're talking about, but this is really like free improvisation, lots of bruitist, like noise kind of noise making with the trumpet or stuff like that. So this is impossible to recreate. And it's not just the music, it's the whole thing. The audience, the day, the state of mind, the mood, everything is in there. So documenting that is, is really complex, and recreating it, replaying it, just replaying the note would be one part of it, but at least the musician would tell you it's not the same thing. I can replay the same notes, of course, but it's never going to recreate the experience as a whole. And as for us, I mean, we're not, well, I mean, yeah, we would see something maybe, but I mean, the thing is, the retrospective rating for which we are analyzing the data only makes sense with the experience. It doesn't make sense if we replay it. Second thing, what you suggest has been done previously in the literature, actually. So that's the classical improvisation studies in fMRI or EEG is actually, I mean, comparing what happens when people play by reading, like audition, or not audition, but like reading a score, or play something by heart, or improvise. So there's been like numerous studies which are already like summarized in reviews and things, with this kind of paradigms where like you try to compare brain activity during improvisation or during recalling from memory or during like sight reading, and
So they play
people have shown that
exactly
it's
the same
different
thing.
things going on. Yeah, different brain networks, like more activation in certain parts of others. I don't have all the results on the top of my mind, but that's the classical, let's say, reductionist approach to improvisation would do that.
Okay.
Peter would probably be able to jump back on that and say something different, but if you want to launch a debate, it's already there.
I would say that I completely agree with you. Even playing the same notes as you do in an improvisation is sometimes impossible. I mean, because yeah, it just happens. So it's a tough. That was also why I was very interested in that part, because that is one of the toughest things that you can do with neuroscience. Because creativity in all kinds of neuroscience, you need 20 participants at least, maybe 40 that are doing the same thing, and creativity wouldn't be creative if they were doing the same thing. So it's yeah, it's a tough. We have tried a couple of approaches. Earworms is slightly tougher, but
Okay. Maybe a last short question. In the figure 2.5 or your document, you give the correlations between the different outcomes from Basta tasks. And you explain that you say the outcomes of duration discrimination and the adaptation to slower and faster tempi were isolated from other outcomes, suggesting a distinct underlying mechanism. Well, I agree with that. You said also that the perceptual threshold for anisochrony detection with tones were positively correlated with tapping accuracy and variability. But actually, these correlations were about 0.6, 0.7, or minus 0. And it seems to me that it's quite low. Maybe it's significant, but quite low. And could you really say that the underlying mechanisms are related with solo correlations?
I mean, we're talking. I have a figure. Yeah.
I
should look at the exact numbers to be sure, but yeah, it's not more than 0.5 for sure.
The 2.5, it's a square with a lot of colors.
Yeah. I have the figure in front, but I'm not sure I can read easily the legend with the
Yes,
the magnitude of the correlation itself. I mean, it's definitely significant, because otherwise it would be white, be filtered out. So it's been a little while I didn't look at the literature to remember if there are other evidence from the literature that suggests that anisochrony detection predicts variability in tapping, but I wouldn't be surprised. I think Simone Dalla Bella has reproduced this a few times, and I think because I asked him a question when preparing this figure because there was one cell that was missing, and he sent me the correlation value, and he told me that he had like a lot more data that confirmed some of this correlation, but the paper was currently under preparation. So it might be stronger than that.
Okay. Thanks.
But that would be interesting because I would also answer one of the questions that Serge asked earlier, because that's like anisochrony detection is just perception of a very slight change, and tapping is a more like sustained motor activity, which is the different time scale. So that would indicate a link maybe between these different time scales.
Okay, thank you. So now the committee is going to quit the WebEx.
Okay.
And we meet on the Zoom link I sent earlier. And we come back here.
Yeah, I'll stay online.
Quarter, yes.
I stay online. Thank you.
Okay.
Okay, see you.
Okay, see you soon. Je vois encore Peter, mais je pense qu'il... Mathieu, tu peux prendre le micro. Ah non, il met un petit moment à se rallumer, c'est normal.
Tu m'entends?
Ça y est, je t'entends. Je sais pas si... ouais, tu peux arrêter le stream. Je sais pas s'il y a moyen de faire pause, mais
J'arrête
bon,
le
c'est pas grave.
stream? Il y avait une vingtaine de personnes là.
D'accord. Bah, sinon, on peut faire pause et puis remettre quand ils reviennent. Je sais pas si c'est possible.
T'as un message de Jean-Philippe Farrugia.
C'est mon frère.
Du coup, ouais, j'arrête le flux?
Ouais, arrête-le.
Ok.
Et ouais, maintenant ça sert à rien. Si on le remet, je sais même pas si. Bah non, si tu l'arrêtes sans YouTube, il va compiler la vidéo là, donc c'est.